One of the very nice things about focusing on the angular components of these equations is that their close relationship to the angular momentum gives us really a physical model of what these functions are that we are solving for. Now, these functions, I've chosen to write them down as y because in the literature and in future courses, there's a standard name for these. These are something that are known as the spherical harmonic functions. And these spherical harmonic functions are often introduced as these special mathematical functions, but as we can see, they represent nothing other than the pure states of the angular momentum. And what's beautiful about that fact is that then we can have a physical model for what these functions represent. So that rather than having sort of these mysterious special functions y that have all these interesting properties but not knowing exactly where they come from, by having a physical model, it gives us physical intuition as to what the underlying properties of these functions must be. And I do have to say, as a practicing physicist, although I've used these spherical harmonic functions very often, it turns out that because they obey so many very nice identities, there are things like the addition theorem of spherical harmonics, and these obey various sum rules, for example. There are all these very nice identities that you can just pick up from having a physical intuition without actually having to know what these functions are. The truth of the matter is we almost never need to actually determine one of these functions. We generally just use its properties, such as the allowed values of a. So I'd like to give you an idea of what this physical model is and show you some of the power of having a physical idea of these spherical harmonic functions. So our physical model is simply as follows. If you look at our equation, it's describing something that looks like a particle that's moving around with just two coordinates, theta and phi. So if we like, we can think about a point mass m that is a free point mass, but it is constrained to move around on the surface of some sphere. If we think then about the Hamiltonian of the system, because we're not going to be applying any external forces, what we realize is that that Hamiltonian is nothing other than the kinetic energy operator. And the kinetic energy operator, as we'd seen in the previous lecture, for a particle that's just moving around at a fixed radius, is directly related to the square of the angular momentum. So there are then certain properties or expectations that we can have now that we have this physical model. So the first expectation that we see here is that these so-called spherical harmonic functions, which again are traditionally written as y, which depend on angles theta and phi, they are just pure states of the energy or of the Hamiltonian, right, for are the pure state, I should say, they are the pure state wave functions, actually. Wave functions, right? Because that's what they are going to give us when we solve that Hamiltonian equation. They are the pure state wave functions for a free particle, right? There was no potential there on a sphere. Now, we know some physics that teaches us some interesting things about those functions. The first thing I'd like you to notice is that this particle is moving about here in a finite space on this sphere. And because it's moving in a finite space, its orbital periods are going to be finite. And therefore, just like we find normally in bound states that are bound into a finite region, we expect there to be a discrete set of solutions. So these actually come with a discrete set of solutions. Right? And we can count them out in various ways. We can give them some kind of an integer index. The traditional way, the traditional labeling for these states is not actually to give them just a single integer index, but two integer indices. So we traditionally label them by L, an integer L, and an integer M. So they're often written down as Y sub LM. And the way these labels work is that L can take on any non-negative integer, where L goes from 0, 1, 2, etc. But then M is restrained in values. It also counts as integers, but it starts at minus L, then it goes up 1, minus L plus 1, etc., minus 1, 0, 1, etc., up to L. Now, the reason why the labeling is this way is a little bit mysterious at this stage. I'm not asking you to accept this on faith. We will be proving this pattern here a little bit later on. I just want to make connection to these well-known functions, the spherical harmonics, and how they're traditionally labeled. One thing I can make plausible for you, however, is notice that the YLMs, right, they solve a Schrodinger equation with this operator. And this operator, notice, has two different variables associated with it. So in the long run, what one could do, we're going to take an operator approach instead. But what we could do is solve this partial differential equation by another separation of variables. And then there will be an integer index for the phi solutions and an integer index for the theta solutions. And that's why we actually end up with a pair of integers. It's simply because we have two dimensions in our functions, and they end up being two different integer labels. Well, it's nice that there's a discrete set of solutions. There's something else that we know we can do, because we know that there is an energy representation. So by the quantum principle of superposition, which comes to us from Dirac, right, we know that we can express any function, right, that represents any wave function, right, as we could represent it in the energy representation for this effective model that I have. And if I write it out in the energy representation in a quantum principle of superposition, all that I'm saying is that any function whatsoever, f, and leave a little bit of space here in your notes because I'm going to insert something here in just a moment, but any function that depends on theta and phi can be expanded out in terms of these pure states of the energy. They happen to be labeled by L's and M's, and we will show you how that works a little bit later on, with some weights, right? Some weights, W, which depend on L and M, and leave again here a little bit of space in your notes, times our pure states, which are these Y, L, M, theta, and phi, right? That's just a known fact from the quantum principle of superposition, and this means then that any function that's reasonable to us, by which we mean again functions that are completely continuous and their derivatives exist and are continuous. These are so-called C infinity functions that exist on the sphere and are square normalizable. Those then make up the kind of physical states that we're talking about. Any physical state could be represented in an expansion like so. Now, here's where I want to make an additional observation on this. I'd like you to notice or think about this for a moment. Suppose instead I actually had a function that depended on the full three-dimensional space. So perhaps it actually happened to have depended upon R. Now, if you just imagine for the moment covering up this R, right? Take one value of R, some particular value like 13, and if I look at f at 13, stick in 13 for R, what I'm left with then is just a function of theta and phi. And I know that this expansion that I'm showing you is going to work, right? Because what I'm looking at is just a function of theta and phi. There'll be some set of expansion coefficients. Now, the expansion coefficients that I get for one value of R will certainly be different from another value of R, right? If I go to R equals 15 and just set this constant equal to 15, f of theta phi, I can expand it. It's just a function of theta and phi. But these weights now will be different, and they will simply depend on the radius that I've chosen. So in fact, any full three-dimensional function can be written down as such a superposition, any reasonably behaved such function, where the weights happen to depend on the radius. Now, the particular application of this is as follows. So one application I can make of this is to say, okay, let's take a solution, any solution, right, to the time-independent Schrodinger equation, right? That would be some function psi of R, theta, and phi. And I can certainly expand it in an expansion in this form. As we've seen, any function could be expanded that way. And I could write this then as a sum over Lm, some set of numbers that depend on R and the index Lm. And I'm going to very suggestively call that capital R sub Lm, which will depend on R. This is just a different way of naming the weights from the quantum principle of superposition times these YLM functions of theta and phi. And why I do this is that what I want to stress to you is that we had made a key assumption in our separation of variables. We had assumed that when we said we're going to seek solutions in this particular form, we had assumed that any solution could be written this way, right? Otherwise, there might be something that could fall between the cracks that we may not find because we were only looking for product form solutions when we did the separation of variables. Now, though, we can see that any function actually can be written down as a superposition as a sum of products of exactly that form. So in essence, this is the reason why we aren't missing anything from our separation of variables. Later on, we can show, if you have an interest in this, you can show that these actually satisfy equation 2. They must satisfy equation 2, and that is why, in essence, the separation of variables approach works. So that gives you some idea of the expectations and ideas, right, that can come to us directly from having a nice physical model to give us some physical intuition as to what these spherical harmonic functions actually represent. They represent physical quantum states of a particle on the unit sphere.